Hi, welcome back. So today we'll be still talking about sound. So last time we talked about sound as a wave, and our hearing is the perception of sound. So as sound is generated by a source and then propagate in air, it pushes back and forth the medium, the air molecules, so that it creates density variations as a function of position, and then also pressure variance as a function of position. So sound is a wave, so you can still use the major quantities to describe sound, the wavelength, period, frequency, and the speed of sound. And the speed of sound is actually proportional to the square root of the temperature of the sound in medium. And for example, in air, so that's related to the speed of the air molecules in air, okay, as well as the same as the room square of speed of the air, or similar to that, proportional to square root of temperature. So sound wave pass through a cross-sectional area. Its intensity defined as energy divided by area times T. And because power is energy divided by T, so then the intensity could be also expressed as the power divided by the area. For a point source, the intensity then is P divided by 4 pi r squared, because area for if you are distance r away, then the um, wave intensity at that point is spread over the spherical area of 4 pi r squared. Okay, so 4 pi r squared, the spheres of it. Our ears hear the sound intensity as a intensity level defined by this equation beta equal to 10 dB log of 1 over I naught, the threshold of our hearing, 10 to the minus 12 watts per meter square. Today we'll be focusing on the Doppler effect. So you probably know that Doppler effect is used very often in astronomy to study the speed of a distant star. If it's moving towards us or away from us, you probably hear them associated with the red shift or blue shift of the star, right? So if it's um, a red shift, then that means it's moving away from us. It's a blue shift that's moving towards us. Okay, so similarly here, for the sound, if you are staying on the side of the roads, if the car is moving towards you, you hear higher pitch, which is corresponding to the blue shift, higher frequency on the spectrum. And then if the car is moving away from you, you hear slower pitch. So it's moving away. The frequency is become smaller, which means it's moving away from you. Okay. So basically, as the source is moving towards you, let's take a look at the scenario of towards you, then the source gives us a sound wave. Okay, so let's use these circular lines as the wavefront it gives out. Okay, so as it emits the wavefront, so the first one could be given at this point, the original source position, and then as it moves, after a period of the sound wave, it's moved to the position 2. Okay, so then it gives the second wave. Okay, so in that sense, so as the observer standing here, it hears the first wavefront, and then the second one will take less time to reach that. So it appears to the observer that the period of wave is becoming smaller and smaller. Okay, so then the wavelengths the observer hears as then the speed of sound times the period, now plus the speed of this source. Okay, so US for speed of source, V for the speed of sound. Okay, in this equation. In the other scenario, if the source is moving away from you, so then appears to the observer that the wavelength has been or enlarged. Okay, it becomes longer. So then the wavelength, or actually in the first case, sorry, in the first case, when the source is moving towards the observer, so the wavelength becomes smaller. So you take the minus sign. Okay. And if the source is moving away from you, you take actually the positive sign, the plus sign. So V plus of US times TS. Okay, so the plus for the source moving away from the observer, minus for the source moving towards the observer. Okay, in that sense. And period is 1 over frequency. You can also write in this term. Okay, so this is the wavelengths appear to the observer when the source is moving either towards or away from the observer. So the frequency then here by the observer will be the frequency divided the speed of the sound divided by the wavelength. Okay, so then speed divided by this term. So then you get this. In terms of t, it's 1 over v, so divide by 1 over v, 1 over f, so then the f flips to the top, okay? So then fs. So it's v over v plus or minus us, and then again, plus for source moving away, and then minus for source moving towards the observer, okay? If you divide by both denominator and numerator by v, so then it becomes 1 on top and then 1 plus minus us over v at the bottom here, okay? So then this is the equation you use for the scenario of that if the source is moving and the observer is stationary. And also the mathematics you can actually see from the geometry here in this figure, okay? So it appears that the source, if you are the observer on this side, source is moving, approaching that guy, so the wavelengths become smaller, okay, use that one. And then if the observer is on the other side, the source is moving then actually away from it, okay, so the wavelengths become larger in that sense, so in that case. All right. So for the first example here, it says a bat moving at speed of 3.25 and emitting sound of 35.0 kilohertz approaches a moth at rest on a tree trunk. What frequency is heard by the moth? If the speed of the bat is increased, is the frequency heard by the moth higher or lower? And calculate that frequency heard by the moth using this newer speed of the bat, okay, 4.25. Use the speed of sound as 340 meters per second. So in this case, this is the bat is the source, right? This is observer is stationary. The source is moving. Now it's moving towards, right? So let's take a look on the equation. It's moving towards, so you'll take minus, okay, from this equation. So you can write that down. F by the observer equal to 1 over 1 minus U of the source divided by V of the sound, and then F of the source. Okay, let's take a look. So the equation to use F, so for part A, by the observer is 1 over 1 minus U of the source over V, speed of sound, times Fs. Okay, so you plug in your numbers, 1 over 1 minus 3.25 meters per second for the speed of the source, speed of sound 340, and times the 35 kilohertz. Okay, so all this put together. So that gives you 35.3 in kilohertz. Okay. All right, so B is asking you if the U of S increased, right? So if this increased, but this is a minus sign, so the whole denominator should decrease, right? But 1 over that should still increase, okay? So it looks like we should be getting a frequency that will be increased, okay? So, or higher pitch, okay? Increased or higher. And we'll just repeat what we did in part A, right? So f of 0 equals to 1 over, now this becomes 4.25 meters per second over 340 meters per second, and times the 35 kilohertz. Okay, so that gives you 35.4 kilohertz. I think it's given 35.0 kilohertz in the question for the significant figures purpose. Okay, all right. Let's go back into the slide. All right. So now let's look at the different scenario. So if your source is stationary, the observer is moving, right? So you can think about this as you approach the source, right? Observer approaching the source. So again, each wavefront here gives out by the source, right? It's arriving at the observer appears to be actually having short wavelengths. Okay, so the wavelength is reduced. Okay, so in that sense. And if this guy, as the observer is moving away, then it's the other way around, right? So the wavelength appears to be increased. Okay, so in that sense. All right. All you can think about this. So if moving receiver, right, it's approaching, right? So then the wavelength becomes shorter. Okay, so that's the new wavelength, or the wavelength appears to be the receiver, right? If it's moving away, then it's the other way around. So at the end, you get this equation. F of 0 equals to 1 plus minus u naught over v f or uf of 0, and then times fs. Okay, so in this case, if the observer is moving towards the source, then the pitch will be higher, the frequency heard by the observer will be higher, so you take a plus. And when it's moving away from the source, you'll take the minus sign. Okay, so that's the case there. All right, so let's take a look on the example here when it says when the bell in the clock tower rings with a sound of 475 hertz, a pigeon roosting in the belfry flies directly away from the bell. If the pigeon hears a frequency of 448 hertz, what's the speed? Use the speed of sound, again as 340. Okay, so let's take a look on this one. So we'll be using the equation then this guy here. Okay, so f of O equals to 1 plus minus. Now in this case, the O, the observer flies away, so away you'll take minus. Okay, so then 1 minus UO over V times Fs. Okay, so now we'll take a look on that. Now the equation to use is F sub O equal to 1 minus UO, U sub O over V, and then Fs. So 1 minus, or actually, we have this guy given 448 hertz equals to 1 minus UO 340 meters per second and 475 hertz. Okay, so divide both sides by 475. A little bit of algebra here. 475 divided. So cancel there, and this would become you rearrange the terms, so 1 minus times 2. 1 minus 448 over 475 equals to UO over 340 in meters per second. Okay, then 340 times both side equation here and here as well. You'll get rid of 340 there. So that gives you your U sub O equal to 19.3 meters per second. Okay. All right, so this is the case when the observer is moving, but the source is not moving. Okay, let's go back to the slide. All right, so you don't necessarily always have either the observer or the source being stationary, right? It could be both are moving. So if that's the case, then the two equations previously we saw combine. So then it becomes this one equation. So frequency received by the observer is equal to then the speed of sound plus or minus the observer speed, and then divide by the speed plus or minus the source speed, Fs. Again, if the observer is moving towards the source, then you get the plus, okay, because frequency will increase. If observer is moving away, you get minus. On the source moving part, if the source is moving towards, you get a negative down here, but plus when the source is moving away, okay? And also the Doppler effect has many practical effect or the applications like speed radar, weather radar, medical, and astronomical measurements, etc. So let's take a look on the speed radar. Okay, so it says a motorcycle and a police car moving towards each other. So they are both moving towards each other. Okay, the police car emits sound frequency of 523 and it has speed of 32.3. The motorcycle has speed of 14.8. What frequency does the motorcycle here, cyclist here? Use the speed of sound as 340. Okay, so the two move towards each other. So let's take a look on this equation. On the numerator, you'll take a plus. On the denominator, you'll take a minus. Okay, so then you'll use that equation and then you calculate what will be the F sub O. So let's take a look. So as I said, FO on the top, you'll have V plus, okay, U of O, and then at the bottom, you have minus U of S, and then times F of the source. Okay, so speed of sound 340. So they are all in meters per second. So I'll just skip the units here. Okay, but they are all in meters per second. Minus U of O, it says, is 14.4, 14.8. Plus, sorry. On the bottom here is 340, but minus 32.3, okay? Times 523. So you should get 603 Hertz by the motorcycle, okay? Now this is just part of the real life application, right? So if, let me go back to the slide. In the real scenario, right? So the frequency given out by the car, by the police car, will reach the motorcycle and then be bounced back, right? And then be received by the car to determine if this guy is speeding or not, right? So then after we calculate the frequency heard by this guy, the sound frequency heard by this motorcyclist, then it will bounce back. Now this becomes the source at the 603 Hertz, okay? And then this becomes the receiver. So you will apply the Doppler's equation one more time to get the speed or the frequency bounces back to the motorcycle or the police car, and then the police will then determine if the motorcycle is speeding or not in that sense. Okay. All right. So now, if we look at this equation previously here, okay, so if the source is moving towards the observer, right? So then we take a minus sign. So I think it's fine for this observer, right? The speed of observer, no matter what speed it is, but for the source, it would have a problem if this guy is the same as V when you take the minus sign, right? So then this then becomes 0 in the denominator. Okay, so then there will be consequences if that happens. So when that happens, it's called sonic boom. Okay, so if you plot the equation, you'll see if the speed of source is approaching the speed of sound, then it actually will blow up the frequency, okay, in that sense. So what happens is the source is moving faster or equal to the speed of sound, okay, so then it will no longer receives as the own sound in that case, okay, so then there'll be sonic boom when all these are pressed together, okay, so there's a video you can click on here and then see it has the full explanation of what we learned today on Doppler's effect and then how sonic boom is created. Okay, it's a very fun video to watch. I'm sure you can learn a lot of things, so make sure you do that. Okay. We'll stop here for today then. Okay, we'll come back at another time. See you guys.